Hi, in this screencast I'm going to walk you through project 3 and give you some hints along the way. Here's the PDF for the project. You can find a link to this PDF on the assignments page of the course website, and on that page you will also find a link to the zip file for the project, and when you download and extract that zip file in your computer, you're going to see a folder such as this containing these files in it. Okay. So as usual, the folder contains the starter files for the problems in the project. It contains a report.txt file that should serve as a template when you write your report. It contains runtests.py that you should use to test whether or not your programs meet the input and output specifications. And then it contains this folder called data that has several sample input files that you should use to test your solutions, okay, for the problems in the project. So now let's walk through each of the problems in some detail. So the purpose of this assignment is to implement what is called the autocomplete functionality, okay, where the idea is as follows. So let's say you're given a set of n strings, and each string is associated with a non-negative weight. All right. Now the goal is to find all the strings in the set that start with a given prefix, and you want to report these strings in descending order of weight. Okay. So this is what we call the autocomplete functionality. Now this is an important feature in many modern applications. So for example, IMDb uses it to display the names of movies as the user types in IMDb search bar. Search engines like Google use it to display suggestions as the user enters queries in Google's search bar. And then smartphones use the autocomplete feature to speed up text input. Okay. Now in all these examples, the application predicts how likely it is that the user types each query, and then it presents to the user a list of the top matching queries in descending order of weight. Okay. Now the weights are determined by the application from historical data. So IMDb uses box office revenue for movies to compute the weights. Google uses the frequencies of search queries from its users in order to compute the weights. And then a smartphone uses the typing history of the user in order to compute the weights. Okay, so the weights are essentially determined by the application from historical data. Now, for the purposes of this assignment, you're going to have access to a set of all possible queries and the associated weights, and these values are not going to change. Okay, so they'll remain static. All right. Now, any application that implements the autocomplete functionality needs to do so in a fairly efficient manner. So for example, if you're searching for something on Google, for the results that come back from Google to be useful to you, they have to come back from Google in a very short period of time. So Google roughly has something in the order of 50 milliseconds to return the list of suggestions for it to be useful to you as the user. Okay, and in addition, Google needs to perform this computation for every keystroke that you type in the search bar, and it needs to do that for every user that it has. Okay, so it's obvious that the autocomplete functionality has to be implemented in a very efficient manner for it to be useful to the user. Okay. So in this assignment, your goal is going to be to implement the autocomplete functionality, and that is going to involve 3 steps. So you first sort all the search terms or the queries in lexicographic order, and then you use binary search to find the set of queries that start with a given prefix, and finally you sort the matching queries in descending order by weight. Okay, so that's what you're going to be doing in this assignment. So in the first problem, what you're going to do is implement an immutable comparable data type called term in term.java that represents an autocomplete term. Okay, so an autocomplete term is going to be simply a string query and an associated real valued weight. Okay, now your data type needs to support the API that is shown here. So there are 2 constructors. one that takes a string query as an argument and initializes a term with that query and 0 weight. Then it has a constructor that takes a query and a weight as arguments and initializes a term with the given query and weight. And then it has a static method by reverse weight order that needs to return an object of type comparator that compares terms in descending order by weight. And then a static method by prefix order that takes prefix length r as an argument and returns a comparator object that compares terms in lexicographic order, but only using the first r characters of each query. Okay. So for example, if your queries are called v and w, it needs to compare the first r characters of v with the first r characters of w in lexicographic order. Okay. Now you have to be careful here when v and w don't have enough characters, meaning if they have fewer than r characters, then you need to consider all of v or all of w. Okay. So all right. And then the data type needs to implement the compare_to method from the comparable interface that compares two terms in lexicographic order by query. Now here you should take advantage of the fact that a query is simply a string object. So and that strings in Java are comparable by lexicographic order. Okay. And you can do that also with these methods here. Okay. All right, and then finally the data type needs to support the toString method that simply returns a string representation of a term. Okay. Now when you implement your data type, as usual, make sure that you address the corner cases listed here and make sure that your data type meets the performance requirements that are stated here. All right. Now once you're done implementing your data type, you can test it by running this command on the terminal, which essentially runs the test client that's defined in term, that takes two arguments: the name of a file containing the search queries and the weights, and then an argument k that specifies how many results are going to be returned by the test client. Okay, so here k is 5, and what the test client does is it reports the top k terms in lexicographic order. So that's what you see here, and then it reports the top k terms in reverse weight order, which is what you see here. Okay, so so if your data type is implemented correctly, you need to see exactly these results for these inputs. Okay, so that's problem 1. Now let's move on to problem 2. So let's say you're doing a binary search on a sorted array that contains more than one key that is equal to the key that you're searching for. Right? So in that case, you might be interested in the index of the first or the last occurrence of the search key in the array. Okay, so what you want to do here in this problem is implement a library of static methods called binary search deluxe.java that implements that functionality. Okay, so it has two methods. There is first index of that takes 3 arguments: a search key, a sorted array of keys, and a comparator, and it simply returns the index of the first occurrence of the search key in the array, okay, or -1 if the key doesn't exist in the array. Similarly, last index of takes 3 arguments: a search key, an array of sorted keys, and a comparator as arguments, and it's supposed to return the index of the last occurrence of the search key in the array, or -1 if the key doesn't exist in the array. Okay, so here again, make sure that you address the corner cases that are stated here, and that the functions meet the performance requirements that are mentioned here. All right. Now let me give you some hints on how you may want to implement these functions. All right. So let's say that you have an array of sorted items, okay, that is called A, and that contains these items in it: 2, 2, 2, 3, 3, 3, 3, 4, 4, 5, and 6, and their indices are 0 through 10. And let's say that your search key is 3. Okay, so you want to look up this particular key in this array that contains sorted items. All right. Now, when you do a standard binary search, then this is how you approach it. You initialize an index, a variable low that points to 0, a variable high that points to the last element, and then you look at the middle element, right? Using this variable mid, and then you check how the middle element, meaning a at mid, compares with the search key. Okay, so now if you have a match, that is, if a at mid equals the search key, then you simply return the value of the of mid, because that's where the search key was found. But let's say you're interested in the index of the first occurrence of the search key. So in that case, you don't want to simply return mid right away. Okay. Instead, what you need to do is remember mid when there is a match in some variable. Let's call it index, and then you need to continue looking for the search key to the left of mid. Okay, so you'll set high to be mid minus 1, and you'll continue looking for search key using binary search in the segment that is to the left of mid. Okay, and then at the end, when you're done with your search, you simply return the value of index, which is either going to be the index of the first occurrence of the search key, or it's going to be -1 if the search key is not found in the array. Okay, so that's what you need to do for the first index of the search key. Now, in order to implement the functionality where you want the index of the last occurrence of the search key, you need to do exactly the opposite. So once there is a match of the element at mid with the search key, you simply remember mid in some variable index, and then you continue doing binary search to the right of mid. So in that case, you would set low to be mid plus 1, and you continue doing binary search, okay, on the segment to the right. And then once you have done processing all once you're done with the search, you simply return the value of index, which is either going to be the index of the last occurrence of the search key, or it's going to be -1 if the search key is not in the array. Okay, so that's how you need to handle this problem. It basically involves modifying the standard binary search in a minor fashion. Okay. Now, once you're done implementing the library, you can test it by running this command on the terminal, which essentially runs the test client, that is in binary search deluxe, and that takes two arguments. It takes the name of the file that contains the search terms and the weights, and it takes a key to search for, and it simply returns the number of occurrences of that key in that file. Okay, so for these inputs, where the file is Wiktionary.txt and the search key is cook, it says that there are 3 occurrences of cook in that file. All right. So if your implementation of this library is correct, then you ought to see this for the result for these inputs. All right. So that's problem 2. So now let's move on to the last problem, which is called autocomplete. So here you're going to implement a data type that implements the autocomplete functionality for a given set of strings and weights. Okay, and in doing so, you're going to use the term data type that you implemented as part of problem 1 and the binary search deluxe library that you implemented as part of problem 2. Okay, and what you're essentially going to do here is implement the 3 steps that I talked about before. Okay, which are sorting the terms in lexicographic order, so that's step 1, and then use binary search to find the set of terms that start with a given prefix. That's step 2. And then finally sort the matching terms in descending order by weight. That is step 3. Right? Now, you want to organize your program by creating an immutable data type called autocomplete in autocomplete.java, and you need to support the API that is shown here. Okay, so there's a constructor that takes an array of term objects and initializes the data structure from the given array. Now here you want to make sure that you make a defensive copy of this array into an instance variable that is an array of term objects. Okay, and what that means is you first need to create an array for the instance variable that has the same size as terms, and then you need to copy the elements in this argument array terms into the instance variable array. Okay, so that's what we mean by a defensive copy. You shouldn't simply assign this guy to the instance variable. That is wrong. So what we want to do is make a defensive copy of this array. Okay, because when you do that, then when this data type goes about modifying this array, which it clearly is going to do because it needs to sort the array and things like that, that will not have an effect on the client side. Okay, so that's why it's always a good idea to make a defensive copy of such things. Okay, so that's the constructor, and then you need to implement this method called allMatches that takes a prefix string as an argument and simply returns all the terms that match or that start with the given prefix and in descending order of weight. Right? So it needs to return an array of term objects, and these are all the terms that start with the given prefix and are in the descending order of weight. Okay, so here essentially you're implementing step 2 and step 3 of the autocomplete functionality. And finally, you need to implement this method called number of matches that takes a string prefix as an argument and simply returns the number of terms that start with that prefix. Okay, now here again, make sure that you implement the corner cases stated here and make sure that your data type meets the performance requirements that are stated here. All right, now once you're done implementing your data type, you can test it by running this command on the terminal. Okay, so here the test client that is defined in autocomplete takes 2 arguments: a file that contains the queries and the keys, the queries and the corresponding weights, and then this argument that specifies the number of search results. Okay, so it's 7 here. And then what it does is it takes the prefix strings as input from standard input. Okay, so when I run this command, the program, the test client waits for input from standard in, and I type the prefix m and I hit enter, and the program comes back with 7 search results. Okay, in reverse order of weight. Right, and as you can see, these search results, they're all the terms that start with the prefix m. Okay, and they're reported in reverse order of weight. And then I can keep going. I can type this for the prefix on standard input, and then I hit enter, and then the program comes back with 7 results again. Again, the terms, they all start with this given prefix and they are reported in reverse order of weight. Okay, and then you terminate the program by sending it the end of file signal. Okay, so that's that. Now there is also an interactive version of the autocomplete program that is available to you. It's called Autocomplete GUI. That takes 2 inputs. It takes the name of a file containing the queries and the weights, and it also takes an integer k as command line arguments. And then what it does is when you run the program Autocomplete GUI as follows, it's going to bring up a window that looks like this, and in this window you can type in the prefix strings. Okay, so and this is like exactly what we did on the terminal as standard input. You can do it here in this window. Okay, and as you're typing, it's going to report the terms that start with that prefix, and they're reported in reverse order of weight. All right. So if your implementation of the autocomplete API is correct, then you need to see the right results. Meaning you need to see the terms that start with the given prefix, and the terms need to be reported in reverse order of weight. All right. So let's actually try this. So the way you're going to run this is by saying Java autocomplete GUI, and then the file name. So let's use cities. And then let's say that we are interested in 7 results at most, and I hit enter. So that brings up this window where I can type in the search term. Okay, so let me try M. So as you can see, it comes back with these terms that all start with M, and they're all reported in reverse order of weight. Okay, and then if I type some more characters, so for example MUM, then again it reports the terms that have MUM for prefix, and the terms are reported in reverse order of weight. Okay, so this is essentially like a graphical version of the autocomplete functionality. Okay. And then so that's that, and then you can also select a term from here and then hit search Google, and it'll basically search for that term on Google. Okay, so that's the interactive version of the autocomplete program. Now the data directory that is provided to you has several sample input files that you could use for testing, and I strongly encourage that you try your programs with as many files as possible from the data directory. Okay, now each file has a very specific format. So here I show you one particular file. It's called dictionary.txt, and the first line that you see essentially reports the number of terms that the file contains. Okay, so in this case what it's saying is that dictionary.txt has 10,000 entries, and each entry is essentially a weight and a query, right? So a weight and a query, and so on and so on and so on. Okay, so that's how these files are arranged. So you should try and test your programs with as many files as possible from the data directory, right? And you can use either the terminal version of the autocomplete program, or you can use the interactive GUI version of autocomplete along with these files. Okay, so those are all the problems in the project, and now the files that you're going to turn in are term.java, binary search deluxe.java, autocomplete.java, and of course report.txt. And for writing your report, again as usual, make sure that you use the template that is given to you, and as usual you need to tell me how long it took you to work on the project, and then you need to tell me how you approached each of the problems, and then you also need to tell me here about the people that helped you, and then finally just give me some feedback on whether or not you learned anything from the project, and if you found it to be interesting or not. Okay, so that's the report. And but before you turn in your files, as usual, make sure that you run your programs through runtest.py in order to make sure that your programs meet the input and output specifications. Then make sure that you check each of your programs for style. Okay, so the way you do that is by running this command. And then finally make sure that your reports don't exceed 400 lines, and don't contain spelling mistakes, and don't contain lines that exceed 80 characters in length. Okay. All right, so that's all that I had to say about this project. I hope you have fun with it. All right, thanks. Bye.